welcome to section 6 of chapter on logarithms, this one entitled Compounding the Problem. As you might guess, we're going to be talking about compound interest in this lesson. So basically, you can read through the description and pause it here if you want to read through the entire thing, but basically we're going to be talking about how compound interest works when you put money into a bank and how it grows and eventually you gain interest because of that. So in that second paragraph, it says, you haven't saved a lot of money yet. You only have $100 you want to invest in a bank and take advantage of compounding interest. Basically, it means that when you get interest on that $100, then that interest is added to your account. So you have more than $100 after that. Then the next time you get an interest, you're getting interest on a larger amount. So the percent interest you're getting is more and more each time, because say 5% of 100 is smaller than 5% of $105 after that first interest payment of $5 in this scenario. So it kind of starts to increase rapidly or exponentially, as the case may be. And we're going to be looking a little closer at that idea today. The compound interest formula is what we see in front of us right here. And each of those letters represents a different thing. So A is representing the amount you're ending with after a certain amount of time. R is the annual interest rate that you're being given. And usually that is a percentage as a decimal. So whatever percent you're given, make sure you change it to a decimal first. N is the number of compounding periods each year. Basically, in other words, how many times you're getting interest payments added to your account. So how many times they're giving you a percent of your money back. It's added on to your money. So if it was just one, well, then you'd be getting interest once a year. If it was monthly, you'd be getting it 12 times a year. And that's kind of how that works. And T is the number of years. Something important there to note is that if you were talking about only 6 months, well, you wouldn't put a 6 for 6 months. You would put a 0.5 for half a year. And that is important to remember that this is in terms of years. So there's our intro. We're going to look at two example problems based on that formula now. So we'll leave that formula up at the top while we work on it. So in number 1, our savings account pays a generous 5% per year. Generous because most savings accounts are less than 1% per year because they're very safe investments, for instance. And in this one, first one, we're compounding only once each year, and we're only looking at one single year. And remember, we're talking about $100 from what we mentioned before. So our P for principal is going to be 100 for both of these problems. So essentially what we need to do here is just kind of input everything into our formula. First thing you do is make 5% into a decimal, which is 0.05. So our formula, if we enter in all our numbers into it, would be 100 times 1 plus 0.05 annual interest divided only by 1 because it's one compounding period. And then we're raising it to the power of 1 times 1 year. So in this particular one, we could simplify this, but we don't want to simplify it too much because remember that there's a lot going on in this formula. If we have it written like that, we want to keep it kind of the same as what we're going to do later. Okay, so now if I put that in my calculator, 100, 1 plus 0.05 divided by 1 to the power of 1 times 1. So obviously some of that can be simplified, but we'll just leave it alone for now. And the answer that we get is 105. So we've gained $5 from 5% interest annually. We're not splitting it up at all. And we're only doing it over 1 year. So we gained $5 to end up with 105. This, because when we're only compounding once a year for only 1 year, it's really like we're only doing 100 times 1.05 to the first power. So adding 5% to 100 would be 105. Easy stuff so far. So now we're going to be looking at 20 years now. So for 20 years, obviously our t is going to be different, but everything else is going to remain the same. We're still only compounding once a year, so we'd still have 1.005 divided by 1, but now we're going to have 1 times 20 at the top. So in other words, if we did simplify this, it would just be 100 times 1.05 to the 20th power. So they're giving us 5% back on top of what we have each year. So like for the second year, if we know we have $105 after 1 year, we would find 5% of 105 and add that to 105 to get what we have at the end of that year. So now if we grab our calculator again, we would be doing 100 times 1.05 to the power of 20, and we get $265.33. So after 20 years, we've gained quite a bit of money. We've gained $165.33 on our investment after 20 years. So we've almost tripled our money in 20 years, which is pretty good. So moving right along, now that we've kind of looked at the basics of this, so you might be able to kind of tell that the more times you're compounding periods in the year, the more money you're going to make. And that you could see that by using what we just did and just making n more than 1, because you figure that you're raising it to a power of that compounding periods times how many years it's been. And so we're going to now compare all these together. So we would have the amount of money after 20 years. So the t equals 20 years is not going to change. And we still have 5% as 0.05. And those two things are going to remain the same, as well as our principal amount of money is still going to be $100. So we're going to do each of these. So we're going to do compounding twice a year, 4 times a year, 12 times a year, 365 days a year, and then hourly. So the hourly one is going to be a big number. So for starters, let's do twice a year. So for twice, we would have 100. And then we have 1 plus our percent, 0.05, divided by 2. And then 2 times 20. So if we put that into our calculator, we have 100, 1 plus 0.05 divided by 2, because we're splitting up the annual interest into 2 different times that we're getting it. So we're kind of getting 2.5% interest twice a year instead. And then we are multiplying 2 by our 20 years, and we get $268.51. So you can see, compared to 20 years just compounding once a year right above it on my calculator, we've gained $3 and change on that difference. So we have now $268.51. Now we are doing it quarterly, which means 4 times a year. So quarterly, that is 100. That is 100 times 1 plus our percent divided by 4. And then 4 times our 20 years. Grabbing our calculator, we can put that formula in, divided by 4, and then raise that to the power of 4 times 20. And now we're up to $270.15. So now if we compare that to just once a year, well, now we are up almost $5 from what we were compounding only once a year. Next, we have monthly, our 12 times a year. We'll see how that works out for us. So we have 100, 1 plus the same formula. Again, a little repetitive, but it's important to be careful with this formula, like with any formula that you're using. And then we have 12 times 20 as our exponent, like so. You can see the monthly is the 12, remember? 12 times a year is monthly. So now we have 100, 1 plus 0.05 divided by 12 times a year to the power of 12 times 20 years. Yeah. Power of 12 times 20 years. So now we're at $271.26. So now we're increasing how many times we're compounding. After twice a year, we gained a lot, and then we did a little bit more quarterly, and then just less than $1 after that. So that didn't make as big of a difference as it did at first. So 2 left of this process. So now we're going to do daily, our 365 times a year. So that would be 100. And then 1 plus 0.05 divided by 365 days a year. And then we're raising it to the power of 365 times 20. And we can put that into our calculator now. And doing over 365 days for 20 years. So that has only gotten us a difference on monthly of less than 60 cents difference. So monthly to daily didn't really help us all that much. And now lastly, hourly. So obviously we need to do a little multiplication. Many people don't know how many hours are in a year. So if you do 24 hours a day times 365 days a year, we have 8,760 hours. So let's do this in red. So hourly, our N value is 8,760 times a year. So now we have 100 plus times 1 plus 0.05 divided by 8,760, and then 8,760 multiplied by 20 years. And let's see what hourly will get us. We have 100, 1 plus 0.05 over 8,760 hours to the power of 8,760 times 20 years. And we get $271.83. So if we go from daily to hourly, we only gained 2 cents. And that's with rounding. So we really gained less than 2 cents after only gaining less than 60 cents from monthly to daily. So this is something that's, you can tell, is starting to level out. And that is important for what we're going to be talking about next in this lesson. So moving down the page here. So if you want to pause and kind of read through this for yourself, that'd be a good idea. So now, reading through together, so it turns out the value you found in your compounding problem is 100 times a very famous irrational number named E. And that's what I'm talking about, the 271.83. If you divided that by 100, you get 2.7183, which you can see in this big, long number here. So E is irrational, and it's basically a constant, kind of like pi. Pi is a constant that has to do with circles and geometry. E is a constant that has to do with exponentials. And it is a number that is the same no matter what. So as this levels out, we basically have a number here that is equal to E. And if this was, instead of $100, if that was $1, we would have exactly E. We'd be ending at 2.718, et cetera, et cetera. So now what that means to us is that we can use that base of E to basically see, well, instead of hourly, what if we went to minutes, or then seconds, or every possible second of every possible minute and every possible moment. So that is what's known as compounding continuously. at every single moment, which is actually how some financial institutions take care of their interest rates. And that is a different formula where you can see here P times E to the power of RT. So if you grab a calculator, if you're looking for where E is, so if you look kind of like at a lower button here, the E button is right here at ln, right above it, a little e to the x. So if you push the second button and then the ln button, you'll see on our calculator here, we have e to a power. So if I click 1, for instance, I get e, 2.71828, etc. And that is the number we just saw on our page a second ago. So that long number, we are using e to approximate it. So kind of continuing onwards here. So now in this problem, now that we know what E is, we're going to use that formula. And so now if we look in number 4, we still have some similar things. R is the interest rate as a decimal. And T is number of years. And P is still the principal. And then we got our E right there at the top in this new formula. So in this, we are compounding monthly. If you have a savings account at any bank, Wells Fargo, TD Bank, things like that, usually they do it monthly. And so we're going to compare the amount of money in 2 savings accounts after 10 years, compounding monthly, with the same initial investment, or P, of 500, interest rate of 3 cents. And we're going to see if the first compounding monthly compared to compounding continuously, how different they're going to be. So let's find those two values that they're going to be a little different on our calculator first. So let's do monthly first in blue. So that would be $500, 1 plus 0.03 divided by 12. Since we're doing compounding monthly for this one. And then 12 times 10 years. If we put that into our calculator, 500, 1 plus 0.03 divided by 12, raised to the power of 12 times 10 years, we get $674.68. So different is continuously compounding. So that, using E, would be 500 times E to the power of 0.03 multiplied by 10 years. And we'll see how different that's going to be. So now we're going to do 500, and then I push the second button and then the ln button to give me the E value, 0.03 times 10, and that gives us $674.93. So not too different. We're only getting almost 30 more cents, but any more money, I guess, is a good thing. And so that's kind of the difference between compounding monthly and compounding continuously between 2 financial institutions. In a later part, we're going to look at Desmos with these 2 accounts to see when they would be equal to each other after how much time, or when they might be above or below each other. And that is something that we'll look at a little bit later on. Now, E is something that's widely used for exponential growth and decay, because you figure that like bacteria or other things that might be growing exponentially or decaying exponentially are doing so at every single moment of every single second of every single day, minute, hour, whatever you're talking about. And we're going to be looking at the graph of just E to the power of X. So before we do it, if we make a prediction, what we're essentially doing is basically raising 2.71 to the power of X. So like if I did E to the power of 0, or 2.71 to the power of 0, it equals 1. So we're going to have a similar y-intercept to other exponential equations. We're also going to have a horizontal asymptote on the x-axis like normal, and it's going to grow pretty similarly to if I was graphing 2 to the x are 3 to the x, since it's kind of in between those two. So our domain would be still all real numbers. Our range would still be greater than 0. And a lot of similar elements to other exponential functions. And we're going to look at what that graph is and how the table could be set up for how e will grow in Desmos a little bit later on as well. And that concludes the paper version of this part of the lesson.
We are now looking at the Desmos portion of our lesson. The formula in front of us is the one we used for the first half of our work. We had $100, 5%, and 20 years staying the same. And the n was how many times it's compounded. And we've graphed that here where n is the only thing that's changing. So you could follow along the graph as you're compounding more and more times a year. You're increasing the amount of money you get. But eventually it's going to start to level out as you can see it happening visually in front of us. So if we convert this to a table, we could start out at 1, 2, 4, 12 times a year. And then we tried monthly, 365 times a year. And then we tried hourly, 8,760 times a year. And eventually we could go out to 10,000 times a year. We could go out to 100,000 times a year. And eventually we're going to get to that value of E that we mentioned earlier. If you divide that by 100. So if I change this to be a 1, well, now as you go out forever, well, now we're just getting that E value that we mentioned earlier. And we can compare our two functions together now that we know what E is. Our one function was 500 and then 1 plus 0.03 over 12 times a year. And then we raise that to the 12 times 10. So we got $674.68. And that was different than when there was E involved. And so if we compare that to 500, and then nicely does it, you can just type in the letter E, and then it kind of does it for you. Because of that, that's a nice feature right there. And there you can see how different those two things are on Desmos. And then finally, we will end with looking at E of x. In Desmos, we just can type in E to the power of x. And you can see it looks pretty similar to any other exponential function, but it is a constant that can be used to represent anything that is compounding continuously at every moment. And that happens in finance, it happens in nature, it happens in lots of real world situations that we will explore more of in the coming lessons. Thank you for watching this lesson on compounding interest and the constant E.